Well, so thanks everyone for showing up. Today we have Gharibyan, who is going to talk about Python's lunch and complexity of decoding Hawking radiation, and we're very much looking forward to hearing that story. And the floor is yours, Hrant.
Awesome. All right, and to full screen. Can you guys see the presentation? All good? Awesome. Okay, so as title says, I will talk about the complexity of decoding Hawking radiation and some geometric interpretations of it. And okay, so I will in the first part of the talk, I will give a more introductory background on the holography and quantum information connection that has been kind of a line of research for the past decade. I think that has gave us some interesting developments about understanding the relationship of quantum gravity and quantum information. And second part will focus on a specific paper of mine from 2019, end of 2019, with this co-authors, and it will touch upon this idea how to detect the complexity in the geometry, specifically complexity of decoding Hawking radiation. So, okay, let's. Yeah, I think I'm having trouble. Okay, here we go. So, all right, the first part is the introduction. So, quick background on the holography itself. So, holography was essentially kicked off as a field from a 1997 paper by Maldacena that conjectured a duality between string theory in ADS space. ADS is a negatively curved spacetime in d+1 dimensions. It's a theory with quantum gravity in it, and it's asymptotically ADS. And the boundary theory that has one less dimension, so lives in the boundary of this ADS negatively curved space. And it is a purely quantum mechanical theory. In fact, it's a conformal field theory, it has a conformal symmetry. And specific duality is much more, there's a lot more details to the specific duality in this case, in Maldacena's case, but this duality happened to appear in other contexts, including like SYK and JT gravity, which is like a simpler holographic duality, and various other examples of holography. And the basic idea here was that there is a theory in a d+1 dimensional case which has gravity, and quantities in these theories and the physical dynamics can be fully reconstructed from the boundary. And there was like a dictionary that how different observables in the bulk can be mapped to different observables in the boundary. And this paper of Maldacena became like one of the most cited papers, or the most cited paper in physics. And it certainly had a really tremendous impact in terms of investigating the connection between gravitational laws and quantum mechanics.
Okay, so I've seen this many times, but I've never really understood. I don't work in this area specifically, right? But okay, what I never really understood is why should I care about this, right? I mean, like is the point that you're relating quantum gravity to something non-quantum gravity, or is it the fact that it's d+1 to d dimensions? Like, what's so interesting about this from?
Yeah, I think it's most interesting thing about this that's you have a quantum field theory living in the gravitational space, and then you have a quantum mechanical theory without gravity. So there's the most interesting thing that gravity appears to be as an emergent phenomena from a holographic boundary theory that's purely quantum mechanical.
Okay, yeah, that makes more sense.
And that has fundamental implications to how we think about quantizing gravity.
Yeah, I mean, isn't there this major open question of like having a unified theory of physics and?
Yeah. I mean, eventual goal is to first of all, when string theory was developed, right? Like the goal was that people hope that string theory is a unified theory, meaning that it's a quantum mechanics of strings travel in quantum field theory. I mean, string theory of strings that gravity is an emergent theory in it, but it had so many complications and so limited ways like to predict things in it, such that people kind of like realized that they need to focus on specific examples. And the one example that is very clear how gravity comes out of quantum mechanics is the holographic models. And here you have a string theory that has gravitational limits in ADS space. It has gravitational laws. And then it's fully described, the partition function is fully described by only quantum mechanical theory on the boundary. So it's sort of like everything in this additional dimension is holographically emerges, and it has quantum mechanics and it has gravity in it. So, so that was kind of the...
If you prove this conjecture on this slide, then you don't get the full unified theory, but you get a special for a specific example. It sounds like, yeah?
Exactly.
Okay, good. Yeah, okay, that's exactly what I wanted to know. Perfect. Good.
That's right. Yeah, that's right. I think it doesn't necessarily imply that the string theory is quantum gravity theory and like doesn't really shed much light, but it talks about the specific example.
Perfect.
And like beyond ADS example, like it's very hard to think about how one would map one to the other. Yeah. All right. Okay, let's move on.
May I ask another question?
Yeah, absolutely. Yeah, let's make it more informal. Exactly.
Yeah, am I right that conformal field theories in dimension larger than 2 are somehow trivial, or?
No, they're not trivial. Actually, 2 is somewhat easy to study. 3, like it already gets tricky to study, but it's possible. There's whole like bootstrap industry. There's like numerical techniques. So yeah, certainly they're not non-trivial in terms of actually. The most constrained one is a 2-dimensional, but it's not super constrained. It's still, there's some interesting things happening in there too.
Well, actually, you can say that the higher the dimension, the more constraints, despite the fact that there is less symmetry, because in 2D there is the infinite dimensional symmetry. But in higher dimensions, somehow there are less and less CFTs, right? So I think the current kind of understanding is that more than 6 dimensions, there would be no non-trivial CFT in higher than 6 dimensions.
Right? Okay, so the interesting stuff is between basically 2 and 6.
Yes.
I see. Cool. So the next kind of high-level development in this area was this connection of holography, example of holography to quantum information. And this whole industry of like each from qubits, kind of getting the physics out of information, was kicked off by a paper by Ryo Takayanagi from 2006, when they realized that the quantities between the boundary theory that's quantum mechanical and the bulk quantities that are connected to each other, and those are simple quantities. And in the boundary side, the quantity of interest is the entropy of some subregion in the boundary. Let's say it's B. And the entropy, entanglement entropy of this subregion, which is a quantum information quantity, right, of your field theory, is dual to the minimal surface cutting that subregion. And this kind of established the connection between a geometric object, like a surface in the bulk in this gravitational theory that you minimize, and that measures the entanglement entropy of a boundary subregion. And that was actually the first interesting connection between quantum information objects in the boundary theory and some gravitational geometric objects in the bulk. And there's generalization of this when you have like fields in the bulk, then you have the area piece that gravitate, like that's geometric, as well as hello?
I hear you.
Everything is fine.
Yeah, everything is fine. Yeah, sorry. I wasn't sure it's like froze or not. Yeah, good. And then there's also a covariant version of this, where you can actually define these surfaces in a time-dependent way. And I'm not going to go into the details, but sort of the high-level implication of this, that the curves match the entanglement entropy. Entanglement is measured by areas. And so that sort of like kickstarted this whole sub-industry within the theoretical physics. And the next exciting connection was thinking about the quantum error correction and the space-time slices in holography. So there was this paper like by Harlow, Preskill, and Yoshida and Pastavsky from 2015, and they argued that if you take a fixed time slice in the dual ADS space that looks like a Poincare disk, then you can construct the discrete version of the map between boundary to the bulk, and that discrete version will look like an quantum error correcting code. And they defined like a bulk legs, like tensors that encode the bulk degrees of freedom into boundary, and then how it's pushed to the boundary. And then they also constructed a specific map that maps sub-operators in the boundary to the bulk operators. And that was kind of an interesting connection between quantum error correction map that you can build, like using this tensor construction, and the dual interpretation in the continuous ADS space. And this point of view, like even though this picture is hard to add a time dimension to it, and it's still one of the open questions, it was interesting perspective on how to like think about operator reconstruction and how to think about what is the map actually doing. So the map is sort of an encoding qubits from the gravitational theory to the boundary in a way error correction encodes, and it makes it robust to erasures. And this also reproduced this like Ryuta-Kayanagi formula as well, like that I discussed about in a previous slide. So it was very interesting, like a discrete version of holography that related it to quantum error correction. And the last interesting connection was between complexity and the volume. So one of the standard pictures people like to draw is the Penrose diagram. And here the Penrose diagram is essentially like we have two conformal theories on the boundary, living in these two boundaries. And they are in the state called thermophile double, which is like entangled state for a given like temperature T between left and right CFTs. And basically like the dual like gravitational ADS dual of this would be like two black holes with the asymptotically ADS spaces. The left one is the first ADS space, the right one will be the second ADS space, and they both are connected with a black hole. So if you fall into from the left, you hit the singularity, you fall from the right, you hit the singularity, and there is wormholes basically. If you like look at the Cauchy slice connecting like a spatial slice connecting left to the right, it looks like a wormhole that like shrinks to the minimal size at the horizon and then keeps extending as the time evolves. And this wormhole keeps growing as the time of the black holes between left and the right continue growing. And in 2014, like Susskind and collaborators argued that the growth of this wormhole length corresponds to an object in the boundary theory, and the dual object that will satisfy all the features of the growth will be the complexity. So what the object that would be growing for such a long period of time and growing linearly like the wormhole does will be the complexity of the quantum state. And here the meaning of complexity is basically if you have that quantum state in the end, the complexity will be minimal number of like for a given universal set will be minimal number of gates that you can go from a simple state to that given final state. And the relationship between this complexity of the state and the volume will be the following. Is conjectured to be the following. Obviously, it's really hard to prove, considering it's a very like vague definition in a case of like quantum field theories, because for quantum field theories it's hard to really compute and define and compute the complexity precisely in terms of like quantum gates. But there are some ansatz that capture the growth of complexity. Like Rob Myers and collaborators have developed all this machinery for like measuring complexity in quantum field theories. which in a certain like time regions are equivalent to the gate complexity of the state, to the growth of the gate complexity of the state.
Yeah,
All right,
may you please define what is complexity for just quantum mechanics? Just staying inside the quantum mechanics. So what is complexity? Just to be
so
sure.
Complexity, yeah, for the quantum mechanical theory with the finite Hilbert space, which means like it's n qubits, right? Here is basically the definition. So if we have a state psi left, right, in this case, or like any quantum states on n qubits, right? The complexity of that state is basically minimal number of 1 and 2 qubit gates necessary to build that state from all 0 states. So like how many like simple operations I need to do to get from 0, 0, 0, 0 to that final state. And this is like a kind of relative complexity between that final state and the initial like simple state. Obviously, it depends on the specific universal gate set choice you have. But I think the idea is that we only care about scaling and we don't really care those constant factors that like come into play once you like vary the different gate sets. So up to that redundancy, like in terms of like just scaling of this object with time is basically just minimal number of gates you need.
Hrant, if I may also ask a question.
Yeah.
So far what you've been discussing has been the context of gravity, but have people extended this link between quantum information and gravitational field to other field theories, like electromagnetic field theory or something like that?
Oh, you mean holography?
Holography, yes. Yep.
I think no, I think like in the dual side, you always have some notion of gravity. You have some, like every example we have has an ADS space in it, right? Like in a higher dimensions, there's an ADS space emergent. There is a charged black hole case where you actually have electric fields in there too. Like there's holographic examples where you have a like black hole dual to the boundary CFT, and the black hole can be charged. So, but it always has the gravity in it. Like there's no non-gravitational holography as far as I know.
I see. What would the reason for that be? What's the simplest explanation for why there's always gravity in that picture?
Yeah, I think it's basically like what this seems to suggest is that gravity is really like an emergent theory from the quantum, like fundamentally quantum theory in the boundary. Like kind of gravity is the thermodynamics of the quantum information. I think that's what it is. In addition to gravity, you can have other fields that live in there, but gravity seems to be like kind of a thermodynamic description of quantum information of the boundary theory.
I see. So in some sense, when it's emergent, it can't be avoided in some sense, right? It's not that we can just put it aside and look into it.
Yeah, no, you can't. I mean, it's just a rewrite of the boundary theory, right?
I see. Okay, thank you for that, Ron.
Just one comment. As far as I am aware, there is at least one example where it's kind of a toy model of holography where the ADS theory does not have gravity in it. It's just a scalar theory, and then you can somehow relate it to some CFT on the boundary. I don't know much of details, but I think
is it the 2D version? Do you know, like, is it the 2D that because gravity is topological and then you have dilaton?
No, I think that's a different story. I think that in higher dimensions there is some example.
Like in higher, I see.
Yeah. So I mean, from what I remember, there is no gravity. I mean, it's just a fixed ADS background, and there's some scalar fields on it, and then you can have some sort of analog of holography there. I don't know the details, but yeah.
Yeah, like my impression was that all those examples have some kind of like a non-semi-classical version, like some form of gravity. Like with the dilaton too, like gravity is non-dynamical, but it gives the background for the dilaton like scalar field to couple with it. So it's like, in a sense, because it's curved, it's like gravitational, but it doesn't have Einstein equations, right? Like it doesn't have like the dynamical. But yeah, But I guess in those cases the argument goes a bit differently, that you know, the kind of topology fixes the theory.
Yeah.
Good. All right. Okay, so I think now I will focus on actually the project I worked on. So complexity of evaporating black hole and the Python/geometry. So this is, as I mentioned, one of the interesting developments was the relationship between complexity and the volume of wormholes in ADS-CFT. And here, indeed, there's an interesting construct. And then later, this relationship was extended to like the relationship between action in the ADS space and the complexity in the boundary. But I think for our purposes, the volume conjecture is like totally sufficient. And this suggests that the complexity grows linearly with the volume for a very long time up to exponentially late times. Parallel to that work, there was a paper by Patrick Hayden and Daniel Harlow in 2013, where they discuss a case of evaporating black hole. So here we start with the black hole that was created by like radiation that was collapsed, and then like some radiation that was collapsed, and then black hole was created, and then it continued evaporating according to Hawking's calculations. There's a near horizon, there'll be particle creation, and some of the modes will leave the black hole and they will start shrinking. And then one can collect this radiation into the R degrees of freedom, far away from the black hole. And then after more than half of the black hole has evaporated, it has been argued that all the information, because the whole dynamics would be unitary, all of the information that fell in could be reconstructed from the larger side, the radiation. And however, the complexity of reconstructing that information from the radiation was argued to be exponentially hard in the number of degrees of freedom of the black hole. And this argument, like, it was articulated first by Harlow and Hayden, and then Aronson is like Scott Aronson clarified it, and it had to do with the assumptions about the dynamics of the black hole and the radiation, that it's a mixing, it's some kind of scrambling dynamics. And the other assumption was some like complexity class collapse assumption. So that seems like if there was a mixing scrambling dynamics, like if it was possible to do it polynomially, it would lead to some complexity class like collapse, and thus like the argument seemed fairly like clean, that the decoding of radiation around page time, and page time is the time when like half of the radiation has escaped, and basically after around that time or slightly after that time, it'll be very hard to decode the information from the interior. And in addition to that work, there's the newer argument by Preskill and collaborators like Kim and Tang, where they in fact actually study the radiation degrees of freedom after black hole radiation scrambling dynamics and evaporation. They argue that the radiation degrees of freedom are pseudo-random. So radiation, and what it means is that with the polynomially bounded operators, you can never reconstruct the infallen like objects into the black hole. So this was yet another like type argument of arguing that the decoding Hawking radiation should be exponentially hard. And you know, unfortunately I will not have time to go into details of these arguments and discuss them, but I think from a surface, what is interesting that it gives you some kind of a contradiction between these two pictures relating complexity to volume and this decoding of Hawking radiation. In one picture, like at the page time, only time evolution was for the polynomial in entropy time. So page time is like m cube, and then like it's some polynomial of the entropy time. And then at that time, like none of the volumes inside the black hole is exponentially large. So all this like decoding complexity questions should be, everything should be polynomial in entropy, as opposed to the Harlow-Hayden argument that the decoding should be exponential. So this was like an apparent contradiction that like motivated our project. And the whole idea of understanding the geometric interpretation for the decoding Hawking radiation like was kickstarted with this question.
Sorry, I don't get one
And-
thing on the previous slides. What is the task in the first one that you're claiming takes poly time? No, not this one, the next one. So for the second task was, yeah, okay, you want to reconstruct from the radiation the
radiation.
state, but what was the task in the first one that you claim can be done in poly time?
Good. So it's not a task. This is like a state complexity. This is using like complexity equals action, and this is about like radiation and black hole state complexity being equal to the volume. And the claim is like no volume has grown exponentially big, right? Like all the volume is around page time, like the wormhole volume is polynomial in the entropy. And you know, like we are getting into the task very quickly. I think you're poking in the right thing. It's actually not a contradiction. It's a definition of complexity is different.
Yeah, so it sounds like the first one you're saying there exists a short description, and the second one says hard to find that short description, right?
Exactly.
If I understood it correctly. Okay, good. So now you're
talking
computer science
I'm
language.
going to jump into the next slide. The resolving contradiction is actually trivial, and you will see. But poking into the geometry of the first one is the real question here. Like why? What is the geometric interpretation of the second one?
Okay, good.
But yeah, like let's think about the specific definitions of complexity we have been meaning here. So we call the terms unrestricted and restricted complexity. And what it really means, if you have a maximally entangled state between Alice and Bob, imagine you have like n Bell pairs and n copies of Bell pairs, and Alice and Bob share them. Then you act with some unitary that's like some random circuit unitary or some mixing unitary that like keeps the entanglement almost maximal. Then there's two notions of complexity one can talk about. One is unrestricted, which is minimal number of gates needed to reproduce approximate UAB, but if you allow acting on both A and B and crossing across them. So that would be unrestricted. Gates can act unrestrictedly. Second complexity would be restricted complexity, and this would correspond to actually reconstructing everything from the radiation side alone. And that complexity is the number side alone. So in this case, like on the A. And this is possible approximately because if the UAB still keeps the entanglement maximal, then like you can always, if you have in like final state maximally entangled up to like order 1 corrections, then you can reproduce the entire unitary by action on one side alone. And that's kind of what is happening in the Hawking radiation and black hole case, where you have in one case, this is kind of like a cartoon for it. So if you have a circuit that builds the exact same state by acting on one side, this is the complexity corresponding to the Hayden-Harlow reconstruction question, and the complexity that corresponds to the volume, like the volume complexity, that's a complexity that allows like gates to couple between left and right. So indeed, in a lot of examples, one can be polynomial in the n, which is number of qubits, or the entropy in the case of the black hole, and the other can be exponentially large. So that's sort of like the naive resolution is that we're talking about two different complexities, and one can be exponentially large versus other cannot, and that has to do if there's like gates necessary to couple left and right. So this was kind of a trivial resolution. One case when these two complexities are actually exactly the same is when you have a thermophile double, and then you evolve with this Penrose diagram black hole where there's no coupling between left and the right. So in that case, like the restricted complexity and unrestricted complexity are exactly the same, because there's no gates interacting between the two. So undoing those gates in one side will not be like difficult because they don't exist. But for the case of the Hawking radiation, you actually have a coupling between the black hole degrees of freedom and the radiation degrees of freedom that left. And essentially how that works is like one way to see it is to look at this nice slice inside the black hole. This is like a Cauchy slice, the dashed line. And then green particles are like sort of Hawking pairs coming out at different times. And after each time they come out, they like scramble with the leftover black hole degrees of freedom and they leave. So they are always like coupling between the black hole degrees of freedom and the new Hawking mode dead left. And then in the end of the day, even though entanglement between the two parts is maximal, you still undoing it from one side will be extremely hard. And that's kind of why this contradiction between the two. But what was interesting is like, is there a geometric interpretation to this hard complexity? So is there like a notion, you know, we argued that the unrestricted complexity is the volume, that it like keeps growing the volume and it captures the total state complexity. But is there like geometric objects that knows about restricted complexity? So can you detect this exponential complexity purely from the gravity side? So is there anything in the geometry that's special? And I think the claim we have at this point, and we have some examples where we studied that the wormholes actually between the case when the two are equal or is very different from the evaporating black holes when the two are very different. And in fact, for the thermophile double, when you have like no interaction and the restricted and unrestricted are equal, is the case when the wormhole has like one minima in it. So basically the wormhole grows, it has a single minima, and the volume of this wormhole is the unrestricted complexity, but the restricted is equal to it too. But in the case of the evaporating black hole, we argue that the wormhole actually looks different, and it has this kind of an obstacle in the middle, geometric obstacle, that prevents you from undoing everything from a single side alone. It's like this kind of obstruction that we call Python's lunch. Like, and the name Python's lunch basically means that there's this bulge, the Python just ate a deer or something, and like there is this bulge in the geometry that is actually detectable, and that bulge knows about the complexity of decoding. Good. And obviously for the holography itself, this would be hard thing to compute explicitly, because even like the complexity in the quantum field theories is really unclear how to talk about. But I think the ansatz that we are like kind of fairly confident about is this tensor network ansatz. Basically constructing tensor network that has a Python's lunch in it, meaning that it has this min max mean structure, and try to analyze the complexity of undoing everything on one side essentially, and argue that indeed this is the right notion of like relating to the restricted complexity. So let me talk about this tensor networks. As we argued, tensor networks are like error correcting codes. I think I kind of hear like talking about them like interchangeably, but obviously they're different objects. But in this case, like the toy model is fairly simple. It's like a bunch of unitary gates that evolve starting from some number of qubits, and then you add ancilla qubits at the part when it starts going larger, and then evolve it again unitarily, and then shrink it. And in this shrinking, you basically post-select on each of these points in each, and then you post-select on a zero state with this isometry. And I think the question is fairly straightforward. So suppose we start with like 0 ancillas in ML number of ancillas in zero state. Then we have some input state on the remaining qubits, psi in. Then we have the tensor network unitary. That's this piece here, that unitarily that has a low volume, in this case like polynomial in total number of qubits, and then we post select on MR qubits in the end. Yep, and then we get some final state out. And then the question is that we want to do this unitarily instead. To actually understand the complexity, we need to replace the post selection with a unitary evolution, right? Because post selection is something that geometry is doing, but to properly undo it on the one side, one has to do it with the unitary gates to know the complexity. So the question would be, what would be a general unitary that would map this initial state to this final state in a generic way, and what would be the complexity of this UPL? Good. And then naively, like kind of roughly to estimate the complexity is to think about like what this post selection does. It basically selects one out of the 2 to the m possible states, and then you can simply run it and try all possibilities until you hit the right post selected value. And then if it's uniform, then it should be like 2 to the m trials. So you have to try it 2 to the m times, and then you have to run the same circuits that many times. Yeah, sorry, I'm gonna move the charger that many times. So you will multiply the number of trials sort of naively with the size of the initial circuit. And this is like some kind of a rough idea of like how costly it is to replace post selection, but one can do better than this. And to do better than this, we have to go to like Grover's search strategy. And in fact, we simply construct two unitaries, the U phi that flips the sign of everything except some input state phi. And then we will define the V operator is like a sandwich between the tensor network unitary operation and flipping the sign only on the until like post-selected qubits. And then if you repeat this L times, which is square root of the total number of the post-selected legs, then applying this UPL will actually approximate really well your like post-selected outcome. However, this was a bit problematic. It has like dependence on the input state, so it wouldn't work for arbitrary input state and arbitrary output state. And the way around it, oh, actually, this is very similar to the Kitaev-Yoshida protocol for decoding Hawking radiation from 2017. And they have slightly different strategy, but the fundamental building blocks are the same. It's some version of Grover search, and they post-select on like Bell pairs, and we do it a bit differently for the tensor network interpretation, but very, very close work. However, for us, it was also important to be able to reconstruct everything for any input and output. We had to like kind of think about having a unitary that's independent of the input state. And turns out it is possible to construct such an isometry if you have the input ancillary like qubits number is larger than the output qubit number. So in appropriate limit, when everything scales with the entropy, but one is larger than the other, you can actually only flip the signs of the ancillary qubit rather than entire state, and then use the same strategy, repeating L times the UV block, and then you end up with the unitary that would actually undo the post selection, and the complexity of this unitary will be the square root of the dimension of post selection times the complexity of the initial tensor network. And this complexity of the initial tensor network was actually the one dual to the volume. This was like unrestricted complexity.
So is this this oblivious amplitude amplification protocol that you're?
That's exactly right. We're kind of using amplitude. Yeah, we basically redone amplitude, oblivious amplitude amplification in the context of the black hole physics. Exactly.
Okay, and then so but this map that you're looking for, it's not necessarily unitary, is it? Like the post-selected map.
So I think so as I was describing. It is an isometry from left to the right? Like the tensor network itself is unitary, like every leg here is unitary, except the post-selected legs, which are introduced isometries, and the uncilless, right? Yeah. That's right, like but the middle part, right? Like this guy here is a unitary, like UTN is a unitary.
Yeah, but the post-selection is not, right? So the output.
Oh yeah, for sure. Yeah.
Like the full thing from left to right, it's not clear to me it can be simulated by unitary, like from the input to the full output space. That's what I mean.
Oh, I see. No, it's approximated. And here is the subtlety is that the area like here I kind of like went over it like carelessly, but yeah, you're right. Generically, it's not unitary, but it's approximately unitary if all the area terms scale with S, and ML is larger than MR, and they are like proportional to S. So in 1/S as like system, basically if you have a black hole where like all the differences scale with the area and area is large, and like it's approximately unitary in like 1/S.
Sure.
So it's like kind of like a large N limit behavior.
Okay, interesting. Okay, good.
Yeah, and the idea that can you do it? I think one question you can, complexity is like this minimal circuit. I gave you one construction for the oblivious amplitude amplification in appropriate limit that becomes unitary. Then one question is this the optimal way? And I think like if the tensor network is like UTN is scrambling, and then it's in fact, if it's like a 2 design, so it's like sufficiently deep random gates applied like in each side, then generically it would not be like shrinkable. So meaning that it would like, if it was generically shrinkable, then it will lead to some like complexity class collapse. But for specific cases of tensor networks, it could be shrinkable. Specifically, if it's not like deep enough, like then you couldn't really argue that there aren't like more optimal ways to do it. But for the generic, like sufficiently deep launch sort of, which is like sufficiently scrambling, that generically you can't do better than this, like a Grover search-like technique. Good. So in terms of like the specific details of how we define, because we're gonna move to gravity soon, how to find the like Python's lunch in the evaporating black hole. Let's maybe like introduce how we find this in a generic tensor network. How would one define this minimal maximal surfaces and number of post selections? In the example I gave, it's very straightforward how many you post select. But in general, I think one has to basically look at the number of the like largest minima, the difference of the post selected, like the number of post selected legs would go like the difference of the maxima and the largest minima. And the finding the minima is fairly straightforward, like minimal number of legs that would cut either left side or the right side. And then there would be like 2 minimas. But the maxima is a bit more tricky for generic tensor networks beyond this example. This example was very symmetric, and sometimes you can have non-symmetric ones. And we conjecture that the procedure one has to use is this minimax, meaning that you look at all possible slicings, find the maxima for each of those slicings, and then minimize over all possible slicings. So like it's the minima of all maximas, and then you look at different like cuttings of slicings of the network, and then find the minimax surface. And the difference between that minimax and the largest minima will be the number of post-selected legs you have to undo. So the conjecture is that the complexity for generic tensor networks will scale like the size of the network times the exponent of the difference. Yeah, this 1/2 factor is like, yeah, the constant factors are like not very reliable here. So the key is that it's an exponential of the area differences, and those would be the prescriptions of finding the 2 different areas that would be relevant. So this is on the tensor network side. And then now let's go back to the black hole and argue why there is indeed a Python's lunch inside a black hole. And for that, I think we have to think about like Python's lunch to be not only geometric, but like rather like this object that measures the geometric piece as well as the entanglement piece in the dual like bulk space. And the way to see, the most cleanest way to see that the Python's lunch exists is to look at this nice slice, but there's also a way to define it without the nice slice in a covariant fashion. And so we have an infalling radiation that forms the black hole, and then we have the Hawking modes coming out again, and then the black hole area keeps shrinking. So this A horizon would be the black hole area in the end. And this basically the black hole interior evolution goes like this. You have like a 1 qubit, and then second, third, and so on, and then the area initially was the large S0 area, and then it continues shrinking as more qubits come out. the two minimas are easy to find. One is like cutting out the radiation legs, and the other would be cutting out the smaller leftover horizons. So this would be, and the page time is defined when the number of radiation entanglement is the same as the area entanglement left over. So when this like wormhole has two minimas, one is only cutting radiation, the other is cutting the area. Sort of like the true entanglement has two pieces, the area piece and the like bulk entanglement piece. So what, and this is like technical term for it is like generalized entropy. And basically like you look at the generalized entropy behavior in this nice slice, and then you can indeed detect that generalized entropy has two minimas. And then the question is, what is the maxima in the middle and how to compute it? And to find the, actually, I must say this minima finding techniques were developed by Aaron Wall, Engelhardt and Wall starting 2014. And there's like it's called like quantum extremal surfaces, and there's this maximum prescription to find it in a covariant way, like when you look at all possible Cauchy slices, find the minimums on all of them, and then maximize all possibilities. So then you can pin down these two minimal surfaces, and then the maximal one is the tricky one. The maximal one is when you actually have to look at all possible slicings going from the radiation to the black hole, and then doing the finding the max, then minimizing it, and then maximizing over all the possible Cauchy slices. And that's the tricky part, because there's two different ways to go from the radiation to the black hole or black hole to radiation. And it is different, like the minimal cuts are different in this both cases, like for these two slicings. But basically it is possible to do, and in general theories it's hard to do, but I think for the examples we study is like which is a JT gravity with the non-interacting fermions in it. This is like the 2D gravity I mentioned that's topological, but you add a dilaton to it to have dynamics. So in this example, when the matter fields are non-interacting with the dilaton, then you can actually like compute this surface explicitly. So there's a maximal surface, and the prescription is maxi mini max for like looking at each Cauchy slice using minimax, similar to tensor network, to define this large surface, and then find the global one. And that gives you this like Python's lunch and each of the surfaces with their areas. And then the conjecture here is that if you have that kind of feature, the restricted complexity of decoding Hawking radiation will scale like the exponent of the area difference of this maximal generalized entropy and the largest minimal. And the way to find those surfaces is given by this prescription, and the first piece in the middle would be the area volume action piece. So this would be like, in addition to connecting like a complexity to volume, this would say if you're talking about restricted decoding complexities, then you actually have to look for this Python's lunch features in the geometry. And then when you have area differences that are sufficiently large, it's like geometry is doing post-selection. So undoing that would be very difficult. So like anything in those regions would be hard to reconstruct, like inside the lunch from a single site, even though information theoretic wise, it is there, like because it's maximally entangled. Yeah. Yeah, this is a bit detailed curve. This is like, and then you can actually compute the behavior of complexity for entire time of evolution, and then like finding the area differences. And it has this funny form that there's page time and half time. Half is when area is actually exactly the half of initial area. The page time is when the radiation and those are two different time scales. Radiation and the horizon are the same. So the complexity like grows linearly, then stops, saturates at this value, and then starts decaying. And then once everything is out, it's also easy again. So even, and this is a calculation of complexity using the conjecture formula and the geometry. So like the Hawking evaporating black hole case was an interesting one, because it has like this radiation degrees of freedom that are quantum entanglement and geometric piece. So you had to use generalized entropy. But I think like Python's lunch exists in other examples where you have purely geometric objects, and even like questions like decoding everything from half of the CFT and the complexity of that will already like see a Python's lunch. And you know, there's all these examples like of Python's lunch when one could actually like study the boundary a bit more carefully, or like dividing the CFT into like subregions and like looking at this transition points. Yeah, so those are like more purely geometric examples of the Python's lunches. And yeah, like there's also another recent paper by Elgenhardt, Pennington, and Mohadan, where like they try to see why is it hard to decode everything inside, everything inside the lunch, and they construct this nice thing of like there's a causal wedge that basically everything inside here can be constructed causally from the boundary, but you can deform it and you can go all the way to this first minima. But all these deformations fail to work once you try to go inside the lunch. So there's like a nature prevents you from like causally reconstructing things inside the lunch, and every strategy fails. It's sort of a additional like evidence that things inside the lunch are protected from easily being visible from one side alone. Yeah, but also I'm not gonna just advertise the paper here. Cool. I think I'm out of time, so I will just quickly reiterate again that like what we did basically is just add additional feature to the volume complexity relation. And the feature is if you have questions about restricted complexity, then you have to modify your volume equals complexity to include this exponential factor that detects this bulge in the geometry. And the naive intuition for this bulge is that it does a post-selection, like nature is doing post-selection. So undoing it on the boundary side in the quantum computation like will require you additional complexity, and that complexity cost will be given with this exponential prefactor. So there are some interesting directions to like continue. Like one of them is like to actually study these features in the quantum field theories and like with this like modified definitions and like of complexity for field theories that are not exactly complexity, but they have some connection to complexity. And another direction that I find interesting is like, is there any use to this to beyond holography? Specifically, like, can you use it for like complexity theoretic arguments and you know, when like geometry gives you a simple picture versus like actual explicit calculation in a complexity space is really difficult and sometimes inaccessible. Like, is it some kind of a new handle? And yeah, and like just studying more examples of the Python's lunches and like yeah, like several examples have been already discussed in the literature. But yeah, I'm also thinking of more interesting like Python's lunch examples. Yeah, that's it. Thanks.
Thank you very much, Hrant. This was a very, very interesting talk. I have to say a bit cryptic, but still very, very interesting. So do we have any questions from the audience?
I mean, I don't have a specific question, but a very general question. So what is like I mean, what are the main questions moving forward for all this ADS CFT stuff? Like, I mean, again, for a non-expert like me, what are you guys really worried about? Like, there are these conjectures, I guess, that you want to prove, basically.
Yeah, I think people are like, it would be nice to prove them, but I think our community is not very worried about proving too mathematically. I think people generally like, there is a general understanding that this information theoretic relationships are poking into some areas that are like fundamentally like can teach us about. I think, okay, let me say it this way. I think like the biggest development was this like replica wormhole story where you can actually show from the bulk that the dynamics of evaporation is unitary, and that had to do with this like Euclidean path integrals and including this additional wormholes and the whole thing like was resolved. Like basically this is like a Hawking and Preskill bet from 1980s, right? Which kind of had all the field like worried about it. It's like, why is the bulk unitary, and can you really like see it from the gravity alone? And the idea was, oh, you can see it. And the whole business came about because people started thinking about error correction, operator reconstruction, Python's lunches, and then in the end they realized, oh, like there's all about decoding questions, and then there was the new techniques developed like based on this generalized entropies that actually shed light what was wrong with Hawking calculations, that it wasn't unitary. And what was wrong is that he missed the second order term, but like nobody realized it until like this picture of like operator reconstruction was developed for like 20 years, right? And the whole development went through error correction. So I think generally people like believe in this subfield that like discovering these connections between information theoretic methods of emergent gravity sheds light on the fundamental building blocks of gravity, like resolving information paradox. In some cases, it turns out to be wrong. Like people thought that you wouldn't really need to know like quantum gravity degrees of freedom to actually know why black hole evolution is unitary, like why Hawking radiation is what should be like corrected in Hawking radiation. Turned out you don't need to. You can do like Euclidean path integral, and you just needed the second order term. And yeah, like it's kind of like just a kind of a belief that if you really try to understand information theoretic features, you can find the final degrees of freedom. I think everybody's after that, like what is the quantum gravity building blocks, like and then you just have little paradoxes and you resolve them, and then hopefully you learn something new, and then you move to the next one. Yeah.
Cool. Yeah, very nice. Thank you.
Any other questions, guys?
So Hrant, at some point you said that, oh, Karapet wants to go. Okay, you go first.
I just have a comment. During the talk, there was a question about why is it that ADS part is always gravity. Just one comment about that. So I found a reference where there is an example studied without gravity, but I can send this reference on the chat. But the point is that, I mean, for most of the interesting theories, non-trivial theories in the CFT side, you would have an energy momentum tensor. If you have an energy momentum tensor, it is dual to graviton in the bulk. So you have to have also gravity in the bulk. In general, whenever you have a conserved current in the boundary, you would have a corresponding field for which this conserved current is a source. So in the bulk, you would have, if you have spin 1 conserved current, you would have also electromagnetic field in the bulk. And if you have energy momentum tensor, then you would have a gravity in the bulk. So usually we have energy momentum tensor. So
yes.
So at some point you were saying that geometry is doing post-selection. You know, could you elaborate on that, like idea more general, more?
So I meant in a sense that, you know, like in the way you found the Python's lines, there's like examples of geometry like two-sided black hole with the thermophile double, where there's just single minima, right? Then the restricted and restricted complexities are the same. But there is an example of the evaporating black hole where actually the geometry, if you look at this generalized entropy, looks like thin, fat, thin. And then the claim was that if you think about it as a tensor network, you know, using this relationship of special slices having like this tensor network interpretation, it seems when you go from a fat part to the small part, like the tensor network is doing some sort of post-selection, right? You're shrinking number of degrees of freedom, probably post-selecting on a specific outcome. So I think that's like, if this analogy is right with the tensor network, like whenever in the geometry you can detect this bulge, it is some sort of post-selection implemented in nature. And like to undo it unitarily, like for example, in the case of decoding things from Hawking radiation using unitary gates, like it would be costly to kind of penetrate that bulge. Yeah, that's all I meant. Yeah, that basically, like if the analogy between special slices and tensor networks is like strong one and holds up in a lot of examples. The implication of this is that somehow that if you have a bulge, you go from the large maximum to the like minimal surface, there is a post-selection happening. And how exactly this geometry does this and what it really means, like beyond tensor network, is still confusing, honestly. But at least like in the case of the tensor network analogy, I'm like fairly confident. Yeah.
Okay, so
that's what it is.
And when you say that it shrinks shrinks degrees of freedom, I mean, what does it mean? Like by shrinking, you mean some sort of tensor,
yeah, like yeah, I think the toy model of tensor network, I had the Python's lunch picture where you have ancilla legs and then you have post select on specific outcomes. So shrinking here meant simply that the minimax surface that you find by like slicing and picking the minimal of all the maximas is larger than the second minima. So there was a more degrees of freedom building up, and then it is like in the end when you reach the subsystem on the right, there's less. Yeah, so it's shrinking on that sense. Yeah. Obviously, on the holography side, we don't really know. Like this map of the Cauchy slices, like fixed time slicing, being dual to tensor networks is very limited, right? We have toy models. We reproduce some of this like features, like Rai-Takayama formula in this tensor network models. But obviously, we don't even know how to define a time evolution of those. You know, like it's you should take this analogy with a grain of salt. But one thing is clear: there's clearly like entropic like features of like min, max, mean, which is consistent for the black holes as well as the tensor network models.
I see.
Yeah, so it's like I think I don't know. Have you guys followed this like replica wormhole stuff like at all? It made a lot of like
Well, for me, it was a bit complicated because I'm not very well versed in wormholes and such, but
yeah, it's also like, yeah, it's very like a sub like community, and it's obviously hard in one talk to kind of communicate, but you know, all this from qubit like interest, like which was pushed largely by like Maldacena, Susskind, and like Shankar and John Preskill partially, like he's still a lot more interested in quantum computing, but there was this like big puzzle, right? Like for getting unitarity in the bulk, and in ADS-CFT, it seems like it has to be, but just purely from the bulk side, it was very confusing how this works, and that's what like was coined like a black hole information paradox. Like how do you show that the gravity is unitary, like when black hole is evaporating? Because Hawking radiation says if you start a pure state black hole, it evaporates, and then you collect the radiation. The Hawking calculation says the radiation will be in a density matrix state. So like it would go from a pure state to the density matrix state. So it cannot be like a unitary. And that like people thought that figuring out this information paradox would lead to a new insights about like how quantum gravity degrees of freedom like operate. But turned out it's not really that easy. It turns out it should be like just a simple correction to Hawking's calculation where you use second order corrections. Yeah, the resolution is remarkably simple, kind of stupid, honestly. So, but like people missed that point. But all this like quantum information machinery was necessary to really pin down what was the problem in the initial Hawking calculation. Like that there was this subleading, exponentially subleading like terms that eventually at the page time become very relevant. So yeah, those are all this
informational stuff is like an interpretational aid to the whole business. Do I understand correctly?
Yeah. In a sense, yeah, exactly. Like all this quantum information picture, like tensor networks, like a reconstruction, like generalized entropy, all this was developed, and then in the end, it led to this perspective of why is bulk unitary, and the perspective was, oh, geez, that's it. And this complexity tools are also like saying which parts of the bulk are easy to construct, which are not. Sort of things that are stuck inside the Python's lunch are not easily accessible from the boundary, like from the radiation. And yeah, and like all this, like eventually, like the big thing, like in, I think it was 2 years ago when the papers came out, replica wormholes. There's like 2 papers actually, one at like Princeton IES and the other at Stanford. Yeah, and they kind of figured it out, like what is the correction to Hawking's formula that has to be added to have information retrieval. But the correction is such a simple thing that it has nothing to do with understanding like quantum gravity degrees of freedom. It's just saying that he missed the second order Taylor expansion in a Euclidean path integral. Just like if he added that, it would get a unitary answer. But like pure things would go to pure things. Yeah.
So how do you see the future for all the quantum informational machinery like in this field? I mean, is it going to survive, or you know, you find this correction and you don't need it anymore?
Yeah, good question actually. I think it will survive. I think there's still problems, but I think this post-selection has to do with singularity. I think there is the idea that singularity is some kind of post-selection, like on a final state projection. And I think what this post-selection in a Python's lunch has to do with that kind of thing. So I think there's a hope that we can actually take it to the new level. And instead of worrying about the unitarity of Hawking radiation, that was like a big question, which turned out not to be that of an important question. Actually poking into singularity, I think that's where the real interesting stuff is. Like, what is the quantum gravity degrees of freedom are hiding in the singularity of the black hole. So the only way to get to it is to really start understanding like what is happening information theoretically at the singularity, and whether is this some kind of final state projection, what are those degrees of freedom, and so on. So yeah, I've been actually thinking about that direction. I think there's a good chance there might be a deeper understanding. I mean, obviously I might be wrong, but yeah, I think that's one interesting way that this machinery, I mean, machinery proved to be very useful. You know, it had a lot of interesting insights, right? And, you know, this paradox wasn't resolved without this machinery in this quantum information perspective. Like it was open and like many people from other like subfield work, but no, it never occurred to anybody to look at the second order term. But certainly, yeah, like certainly I think they're still used to it. Like I think specifically in terms of like understanding the singularity of the black hole.
Interesting. Thanks a lot for this perspective. Do we have any more questions?
If I may also ask another question. So so in the beginning few slides, I think, Hrant, you made a you showed a link between quantum error correction and the conformal. I forget the exact name, but I think if you go back to the slides, I think you know which slide I'm talking about.
Yeah, I know. Yeah, like error correction and the spatial slices. I can share if you want again.
Yes. So I think it was done by Preskel and other people.
Yep, exactly. Yeah.
Yes, this one. So which exact model of error correction would this rely on? Is this like a surface code or something? Like, is there a specific?
Well,
it's
yeah, there are actually several examples. So this happy code is actually fairly straightforward error correcting code. A little more complicated is like a version of this using like Bacon-Shor code. So there's like basically like you have a Bacon-Shor code. Each of these like tensors is like a 5-qubit Bacon-Shor.
Yeah.
And then and then you just tile them in this like in this Poincare disk. So you discretize hyperbolic disk and you fill it up with this like specific tiling. So I think the best example actually where you can reproduce a lot of interesting things is like the Bacon-Shor example.
I see.
But it's not necessarily. I think in happy code it was even simpler. Like the happy code is actually, I think it's maybe it's even a CSS code like mapped to, or it was a 3-qubit. I think it might have been 1 to 3-qubit code. Honestly, I don't remember, but there was some other like very simple code. That was the building block. But then you have some of the traditional building block codes, and then you tile them, and it becomes like a new code, right? Where like the distances, like the operators deeper inside are like have a larger like distance, right? Because they're like kind of deeper buried, so you can erase a lot more stuff without like affecting it. Closer to the boundary, it's like more prone to errors, right? It's like,
I see.
yeah. So it's just kind of a holographic generalization of all this like standard codes.
I see. Okay, thank